everybody from all over. I don't know where all over. I know there's Angola. I know there's Tanzania. There's no South Africa. I know there's Cape Town because our presenter is in Cape Town. So welcome to the second episode of the Concrete Class Back to Basics series of the Concrete Society of Southern Africa. I'm going to start with a short introduction about the Concrete Society, and then I'm going to introduce our speaker, and then we're going to speak about, and then we're going to listen and learn. So firstly, I want to say about the Concrete Society of Southern Africa, as we just restarted after we closed down our doors for a few years, and we are these days focused not only on rules, but we focused on core values and making sure that we deliver the service according to these core values. They are modern and advanced, relevant, streamlined and efficient, objective, inclusive, and loyal. We've got a number of committees going again. We've got the Inland Branch Committee, we've got the KwaZulu-Natal Branch Committee, a Western Cape Branch Committee, we've got a Ready Mix Concrete Committee, which I chair, we've got a FIB Committee, and we've got a Cement Branch Committee, and we are planning to create more committees as we go along to include more of our members and address the needs of our members. Now, events like this seems to be very popular these days. We started with a concrete class a month ago where I presented work on, or presented a class on the concrete mix design method, and that was a record attendance of 61. Now, last week, or was it the week before that, we had a concrete fix seminar that had a attendance of 71. And if some more people join us now late today, this will be the new record because we are on 64 at the moment. So that'll be good. But this is only possible if we have members. We need members of the Concrete Society to participate and, of course, pay your subscriptions so that we can employ staff, that we can arrange events like this for free, etc. This event is for free for the whole world to attend, but if you want CPD points, you have to be a Concrete Society member. But even if you don't want CPD points and you're just interested to support us, please become a member. There's these options. It's quite cheap from a working individual, 1,500 Rand per year. And then you as a company can get the memberships from 3,000 up to a few 100,000 Rand a year. You get subsidy in events that we charge for. And also we've got all these free events we organize. We've got our current members. We've got Diamond members, CRISO and Quick Group. We've got Emerald members, CTS Laboratories and Core Struct. Tanzanite members, we've got 2 screens of members so far. I'm not going to mention each of them, but you can see them. They are supporting the Concrete Society. Thank you very much. And all these companies as well supporting the Concrete Society. We've got a number of associate members as well. And then academic members, which is of importance to today's University of Cape Town because they are presenting this concrete class today. We've got the upcoming event, our gala event we're gonna make it really good. It's going to be the Fulton Awards 2025. That's the 7th of June. If you want to know more anything about that, go to our website, the Concrete Society SA website, to get more information and come join the evening. We've got Concrete Fix. The next Concrete Fix is next week, or the 19th of March on Wednesday. It'll be presented by Dr. Sarah Scorpin and Dr. Megan Brink. It's about the influence of concrete material properties on integral bridge design. Just to mention for those of you that haven't figured this out yet, we've got 2 series, a concrete class, back to basics, and a concrete fix. The concrete fix is to get your fix of the latest technology, the latest research, the latest innovation in concrete. While the concrete class is about the basics, getting to know the basics again as if you were back at university or in a concrete technology class. So the concrete fix for the 19th of March is coming up. And there's more concrete fixes coming in April, May, and June. We're busy lining them up. And then the concrete class is already filled up until July. We have April, the role of aggregates in concrete by Prof. Mark Alexander. We're staying at UCT. Then 8th of May, alkali silica reaction by Janina Kanyi. And then the 10th of July, we're using supplementary cementitious materials by Prof. Rian Kombrink. So be sure to diarize them, but we'll advertise them as well. Come join us for these events. Then the Western Cape branch is organizing a bowls blitz on the 13th of March. It's around the corner. If you're still interested to sponsor or to be at the event, contact Villiers Blom or just look on our website for more information. CPD points, as I said, as we advertised for the first time now, we will only be giving CPD points for Concrete Society members. So if you still want CPD points for this specific event, be quick to register quickly as a member and we can sort that out for you. You will get a total of 2 points per year because we have 10 concrete classes and 10 concrete fixes, each being 0.1 CPD point. So it will give you 2 CPD points a year if you attend all of them. The details, you'll be receiving an email about how to obtain these points and what your code is, but it's like it's written on the screen. And yeah, to follow what we do in the Concrete Society, look at us on LinkedIn, look at us on our website, and you'll see all the exciting stuff we're getting up to. We're really booming at the moment, so I'm really excited for the Concrete Society. And yes, the success of the society relies on the commitment and support of the individuals, companies, and stakeholders from the cement and concrete industry and the wider community. We thank you all for your ongoing contribution. I really appreciate that. So that brings me to why you're actually here. You're not here to listen to me. You're here to listen to Professor Hans Beushausen. He's got a quite impressive bio, and I wanted to shorten it, but I couldn't get it over my heart because all of these things are important. So I'm going to read through it quickly. Hans Beushausen studied civil engineering in Germany and South Africa and completed his PhD in University of Cape Town, working in the fields of repair and rehabilitation and concrete structures. In subsequent years, he broadened his scope of research and teaching from general fields related to structural engineering into service life prediction and performance-based design of structures, steel reinforcement, corrosion, sustainable concrete technology with a focus on low-carbon cementitious binders and recycled concrete aggregates. He's a director of the Concrete Materials and Structural Integrity Research Unit, ComCero, and convener of the postgraduate program on civil engineering, civil infrastructure management and maintenance at the University of Cape Town, and a member of several scientific and professional associations. He's chaired the Rylem Development Activities, DAC, I think as I call it, committee from 2020 to 2024, and was head of the South African National Delegation of FIB from 2014 to 2024. He's currently the Vice President of Rylem and liaison member representing the Concrete Society of Southern Africa on the ACI Committee about Rehabilitation. And I think above all this, he's a member of the Concrete Society, and that I think is probably the most important one. So Hans, we look forward to your presentation. Thank you very much for taking the time in preparing and getting everything ready for this time. We know you're a busy man. Thank you very much. We're all ears and we look forward to your presentation.
Billy Bossoff, thank you so much for your introduction. And also thank you very much for all the good work that you have been and are still doing for the CSSA. And that includes your colleagues, especially also Natasha You guys have been amazing putting this back on track and giving us this experience, or even better than what we used to have. So thank you very much for that. So Billy has asked me to present a short overview on durability and to keep it easy. And I wondered what that really means, because we have a 1-week postgrad course on the topic of concrete durability, overview, materials design, specifications, and all of that. And I tried to now put this together in a short presentation. Billy said I can't have more than 3 hours to present to you today. So I hope I shortened it appropriately and that I can teach you something that you don't know yet. Okay, but he didn't say 3 hours. He said 45 minutes. But if it takes 3 hours, I'm going to blame him anyways. So let's begin. So what you see here is the University of Cape Town. And if you haven't been here yet, or haven't been here for some time, I've seen some names in the lobby there that haven't visited us for a long time. Please come back. Let me find out how to... Here we go. So you can see an overview on the contents of my presentation. I give a brief overview on the different deterioration mechanisms, a bit on ASR, chemical attack, construction defects, and shrinkage cracking. But this presentation will focus on the topic of reinforcement corrosion, which is essentially the main problem we have with our existing infrastructure. And in line with that, I will also talk about the structural engineers' most beloved pet, compressive strength. And I will talk a little bit about why we need to move away from assuming that a higher strength means better quality, because that is not the case in most instances. And I'll give a brief overview on design methods for durability, prescriptive and performance-based. And I will conclude with a little bit of an outlook on the research that we are currently doing. So what I'm presenting here is basically belongs to our research unit. This is all the good knowledge that was developed in ComSciRu over the years. I'd like to thank my colleagues. You can see them on top there, Prof. Alexander and Prof. Moyo. And of course, all our students who have essentially developed all this good knowledge over the years. And looking at our current student cohort, we have about 45 full-time postgrad students at the moment, about a quarter of which are PhD students. And also at the bottom, you see Charles May. He has now left UCT, but I put this figure there to also point out that none of this would be possible without our good staff in the laboratories. So thank you to all of you for your contribution. Yeah, you look at a graph here. On the y-axis, you see the quality of the structure. And on the x-axis, you see the time. So the time 0 is essentially the time the structure has been completed. And then over the years, the performance of the structure will deteriorate. And you can see the red line indicating the assumed service life duration. Typically for normal structures, conventional structures, we design them for 50 years. So if after 50 years, your performance level has gone down to an extent where you have to pay a lot of money to maintain the structure and rehabilitate it, then that's fine. You paid for 50 years and you got 50 years. But in service life design, we assume that within that service life duration, we do not have to spend a lot of money on maintenance and repair. We want to have good performance for the duration of the service life. And what we often see in our structures, not just South Africa, but anywhere in the world, is that the performance that we get is far worse. So the deterioration of the performance takes place much faster. Typically, it could be 10 years, 20 years, 30 years. And then we have to put back the structure into an acceptable level of performance. We have to repair it. And that, of course, costs a lot of money. And typically, you can see here reinforced concrete structures exposed to severe environments, and not even only that, also normal environments often need repair in 15 to 25 years, usually from reinforcement corrosion damage. And then this goes on until your structure does eventually reach its, until your structure eventually reaches its service life end. And one point that I will not touch much on here is that of maintenance. If we were to exercise regular maintenance on our structures, to do inspections every 5 to 10 years, to measure cover depth and know what the cover is, to look for cracks, early signs of reinforcement corrosion, and so on, then we would be able to act swiftly and timely and prevent future damage, for example, by application of surface coatings or hydrophobic sealants, with which we can then prevent significant damage to occur over time. This costs a little bit of money over the service life of the structure and saves a lot of money in the long term. So please consider this. Yeah, and there's no reason for a structure to look like this. Not after 10 years, not after 50 years. If your structure, the bridges, culverts, buildings, ports, look like this after whatever duration, then it means they have been ill-maintained. And we have all this technology available to prevent this from happening. And actually, if you apply this technology early, it's also quite cost-effective. Looking at the mechanisms of deterioration, I've listed here the basic ones. You can have built-in problems. So it means you have a combination of materials that don't work well together. There are construction defects. We luckily don't have many structures that have overloading or design insufficiencies. Engineers are far too conservative to not design their structure properly with all these safety factors. Where we might every now and then have problems with structural capacity is typically when structures might have been overloaded in the construction phase, or when a structure was designed 50 years ago and constructed 50 years ago, when the design loads were much lower than what they are today. For example, it's a typical problem that we have with concrete bridges. And then we have environmental deterioration, physical actions, internal deformations and stresses. I talk a bit about that. Carbonation and chloride ingress highlighted here because those are the factors that cause reinforcement corrosion. Fire damage is more of an accident, but it's something that one needs to be aware of or how to treat it. And then we have chemical and biological attack. So as a very brief overview on these different mechanisms, the most typical built-in problems where you have a combination of materials that gives you problems later when the structure is in service. The two most prominent examples are alkali-silica reaction and shrinkage. So in terms of ASR, we have more and more structures in South Africa and worldwide that are affected by ASR. And it was long believed that ASR just affects the serviceability and it's not that much of a big deal. But in the last maybe 10, 15 years, we have begun to realize that that is not the case. We actually have a massive problem with ASR. That's not just dams and bridges and culverts, but also buildings and iconic buildings, port structures, and so on. So ASR is moving more and more into the focus also of concrete research. And here are some examples of how ASR damage might look like. Here you look at an ASR damaged bridge wing wall, a pre-stressed bridge beam. You can see Devil's Peak in the background and the Dollarser that we have in Cape Town in the harbor. Don't know what they did wrong there, but they all look like this. And here we look at the mechanisms. So you get ASR when silicate minerals in the aggregates react with the alkali hydroxides in the pore solution. So it's a chemical reaction. And in the presence of moisture, this chemical reaction leads to the formation of a reaction gel, the silica gel, which is expanding in volume as the reaction continues. And so in the presence of moisture, this expansion continues, and then eventually this internal growth, which is sometimes also called concrete cancer, can no longer be accommodated in the pore spaces, and then you have internal stresses that can lead to cracking. And once you have cracking, typically also there is a higher chance of moisture ingress, which will then accelerate the whole mechanisms. And looking at, since the focus of this presentation is design for durability, let's just look at the factors that you can consider when you want to prevent ASR. And since we need to have sufficient silica in the aggregates, we need to have sufficient alkali hydroxides in the cement paste, and sufficient moisture. If you can remove any of those three aspects, then you should basically be fine. So looking at ASR prevention, typically this involves the selection of a suitable non-reactive aggregate type, which is not always possible. So if there is a bit of a risk for ASR, you can look at your binders. And the two important factors to consider here are the binder content. The lower the binder content, the lower the problem. And within the binder, of course, the lower the Portland cement content, which is the binder that supplies the calcium hydroxides, the lower the problem. And another solution would be to keep the water out of the structure, which also is not always possible. But if we were to apply, for example, a hydrophobic sealant, I think ASR could be quite drastically reduced as long as we're talking about uncracked concrete. And lastly, of course, there are mixed design rules, and you can also do testing on sample mixes to find out whether you may or may not have an ASR problem. But as Billy mentioned earlier, there will be a presentation by Dr. Kenji in first week of May, and I'm sure she will tell you much more about this than what you've seen now. So moving on to the other built-in problem, that is high shrinkage. And the problem with shrinkage cracking is that it is very difficult to prevent. And I think clients need to understand that a certain degree of cracking is always expected to occur on concrete surfaces, may it be floors or walls or beams or whatever the case may be. But as engineers or as designers, as contractors, there are certain things we can do to minimize the risk of shrinkage cracking. And you can see two graphs here. It's a bit more complicated than this, but the two main things that can be done. If you can reduce your water content in your mix, for example, by choosing well-graded aggregates, by using plasticizers or other chemical admixtures that can reduce water, then you can reduce shrinkage, and therefore also you can reduce cracking. And at the bottom, you see that if you can reduce your strength of your concrete, you can also reduce the risk of cracking. And I will talk a bit about that in more detail in a minute. And the problem with shrinkage cracking is that it's not just bad for the appearance and might not look very nice, but the moment you have severe shrinkage cracking, you allow the ingress of deleterious substances that can lead to, for example, reinforcement corrosion. Construction defects can be numerous, so poor surface quality, low cover depth, honeycombing, poorly constructed hot or cold joints, plastic shrinkage cracking, or just improper steel reinforcement placement, and so on. And all of these construction defects, of course, might again look bad, but the main problem with these is that after 5 years, 10 years, 30 years, they might lead to reinforcement corrosion. So what we do to the concrete in the first couple of hours after it has been brought to site, in terms of placement, compaction, finishing, curing, is really important for the long-term durability of the structure. Chemical attack. Chemical attack is a bit of a special topic, which is mostly important for industrial environments and, for example, concrete sewer pipes. In the background there, you saw a picture of a dam that was attacked by soft water, in which case the attack is normally slow and not very severe. But if you have severe chemical attack, then it is something that you need to design for. And typically, again, this would involve the choice of suitable aggregates, suitable binder types for that particular exposure. And in this case, actually, a higher concrete strength and more dense pore structure helps typically with the performance. And then lastly, this is the focus of this presentation, reinforcement corrosion. So in very basic terms, the steel, when embedded in concrete, is very well protected from corrosion. That is because the high alkalinity of the pore matrix, of the pore solution in the cement paste protects the steel. We talk about passivation of the steel. So if you were to leave a piece of steel lying around in the normal environment, then moisture and oxygen would make it corrode over time. Inside the concrete, the steel, even though it is constantly exposed to water and oxygen, will not corrode unless one of two mechanisms occurs. And the one is the ingress of chloride ions, which is important for example, Cape Town and Durban, or any city or any structure located along the coast. because we have chlorides in the ocean, salts, and if they enter the concrete, we can get reinforcement corrosion, because in that case, that protective layer on the steel is destroyed. And similarly, if you get the ingress of carbon dioxide, where we talk about carbonation, and then together with the carbon dioxide, we have water entering the structure, the concrete carbonates, which lowers the alkalinity. And remember, the alkalinity is the factor that gives us the protection. And once the carbonation fronts or the chloride front have reached the steel, then steel reinforcement corrosion can be initiated. And once that happens, you can see in the background here a piece of reinforcement corrosion, a piece of reinforcing steel that is corroding. Once you have reinforcement corrosion, rust is developing, and the rust is expanding in volume. Again, it's an internal growth in the concrete matrix that can't be accommodated, leading to stresses, cracking, delamination, and spalling. And that is the main problem that we have with aging existing infrastructure all over the world, in fact. And this core sample here shows you actually quite impressively how this rust development can lead to the internal damage that we can see on the structure in the form of a delamination and spalling. So as the rust expands further and further, it cracks open the concrete and leads to significant internal damage, which can, of course, then in the long term affect the structural performance of your structure. And also, once it has come to the point where your structure looks like this, it becomes very costly and difficult to repair the structure and extend the service life properly. And I put this other picture here with the cover measurement. Cover measurements are the most simple NDT method, the fastest NDT method. Anyone can do it. And the main issue we have with reinforcement corrosion is insufficient cover depth. And we shouldn't design structures, for example, next to the ocean or in the marine environment or close to the ocean with a cover less than 50 millimeters. But often we've got 20, 25, 30 millimeters. And with that, we would know that we can expect reinforcement corrosion problems. So if we were to only assess our structures for their cover, which is fast, easy, and very cost-effective, we would know where to expect problems. And then again, we could act swiftly, apply surface coating, for example, to extend the service life. Now, looking at ways to prevent reinforcement corrosion and looking at different design approaches, essentially there are two approaches that engineers can use. One is a prescriptive approach, and the other one is a performance-based approach. In the prescriptive approach, certain mixed parameters are prescribed, typically the water-cement ratio, the cement content, and the cement type. Whereas in the performance-based approach, relevant concrete properties are prescribed. So something that you can measure to actually predict the performance of the concrete. And I'll give you some examples of these two approaches. Before I do that, all these approaches work with environmental exposure classes. So the first step is for the engineer to understand where the structure will be constructed. For example, if the structure is close to the ocean, then you are in the marine environment. And in this table, you see the three basic exposure classes for marine structures. So if you're close to the ocean and west of Cape Agulhas, that means within 5 kilometers from the ocean, or 2 kilometers, I believe. If you're east of Cape Agulhas, then you are in the marine exposure zone. And then we talk about airborne exposure, unless your structure is exposed directly to seawater, from spray water or splash water or in the tidal zone. And then when you design your structure for durability, you follow the recommendations, the prescriptions, or the design rules for that particular exposure class. So the first step is to understand where will your structure be constructed. For example, I always use this example of the stadium in Cape Town, the soccer stadium that was constructed for the 2010 World Cup. I believe it was European engineers who designed it, and I'm sure they were not aware that we have an ocean in Cape Town, because they designed that stadium with 30 millimeters cover depth. I mean, who does that? So it's very important that you look at your structure and the environment to see what are the basic requirements with regards to durability. And then looking at the prescriptive design approach, then for each of these different exposure classes, certain prescriptive requirements are given. And as you can see there, they link to the maximum water cement ratio, they link to the minimum compressive strength and to a minimum cement content. And here you see this in a bit of an extended version. You can see that similar prescriptive design approaches also exist for carbonation-induced corrosion and for freeze-thaw attack, for example, which we don't have in South Africa, but also they also exist, for example, for chemical attack. So for all these different exposure classes, whether it is carbonation-induced corrosion, chloride-induced corrosion, chemical attack, whatever your issue might be, the prescriptive approach gives you limiting values for these mixed parameters. And what you see here is an overview from the EN 206, and our South African prescriptive approach doesn't look very dissimilar from this. So we follow a similar approach. Now, the problem is that the water cement ratio and the strength and the cement content don't really link to durability in the way that it is insinuated here. If anything, then a lower cement content should actually give you higher durability. I will talk about this in a minute. And water cement ratio and strength also don't really conclusively relate to durability. So the rationale for specifying these particular mixed parameters is not really justified. And then what about innovative and economic concrete mix design? What if you have a special admixture or something else that you know will increase the durability of your structure? If you still have to follow these prescriptive approaches, and you can't, for example, minimize your cement content, even though you put something in that will give you good durability, then you are basically prevented from applying any innovation in your mix design. And also, we must move away from assuming that the concrete as placed in the structure will have good durability just because you have designed it to have good durability. So we need to also account for the in situ conditions, for the construction quality, for the placement, compaction, curing, and all of that, which have a huge impact on the durability of the structure. And if you follow a pure prescriptive approach, then the construction conditions can't be taken into account. And lastly, how do we verify the as-built quality of the structure? If we just base our durability design on these prescribed values, how do we trust that we've actually received durability? How can we test that these values were adhered to? So these are all these shortcomings that link to the prescriptive approach. And this approach is still being used all over the world. It's also still used in South Africa for many structures. And there are very few countries where a performance-based approach is being used. For example, in Japan, they're trying to establish one. In Switzerland, they have used a performance approach for some years. And at the moment, they're trying to also include it in all the other European countries. But it's a very, very slow process. In South Africa, this approach was already implemented about 20 years ago. So the performance-based approach, and here you can see the definition of the American Concrete Institute, can be defined as follows. So a performance specification defines required results, which are the criteria to judge the performance, and verification methods without, and this is the important part, without requirements for how the results are to be obtained. So here we don't specify concrete mix parameters, we specify a certain performance. So I say we want this concrete to be having a good chloride ingress resistance. So we want to have a certain performance. If we do that, we need to have some way to measure that. We need to quantify that. We need to specify that. And most importantly, how we go about achieving that is left up to us. We don't have to follow any prescribed mixed composition. We can design the mix in any way possible such that it gives us the required performance outcome. So looking at this principle of performance-based, what is performance-based and where do we know this from? So looking at the first performance-based design and specification method that has been established and that we all know very well, that of compressive strength. So here we take a cube mold, could also be a cylinder. We fill it with concrete, we demold the next day, we place the cube in a water bath for 28 days at 23 degrees. Then we take it out, we put it in a machine, which actually gives us a tensile test, but I'm not going into that. So we call this a compressive test, but the sample fails in tension. And we move these two steel plates towards each other until the sample fails. And we call this compressive strength. And of course, that doesn't correlate at all, or there's no direct correlation with what actually happens in practice, because that structure there that you see there, for which we do this test, has not been placed in water for 28 days at 23 degrees. And it's not also loaded between two steel plates with a very small specimen. But we have learned to accept this performance-based method because we have a very good established correlation between strength and measured on the cube and strength measured on the structure. That's why we can use it as a performance method for design, specification, quality control, and so on. It's the same with concrete workability. We want to make sure we can place the concrete, compact the concrete, that it flows into the formwork, and that we can finish it, and so on. And what do? We test the slump. I mean, the slump has nothing to do with it, really, but we have established a correlation between the slump and workability. It's a totally empirical correlation, not a scientific one. It's a performance test that helps us to predict or to assess, to quantify the performance of our concrete in this particular situation when we want to place and finish it. And in terms of durability, also we have certain test methods. In this case, we measure certain properties of the concrete that can be linked to the ingress, for example, of chlorides, or to the carbonation resistance of the concrete. And again, I want to talk about strength. So because engineers often believe, well, as long as the concrete is of high strength, then we will have good performance. And just to remind you that strength is only needed for structural design, nothing else. And in the structural design process, we only need it for the ultimate behavior, for the ultimate limit state. When you're, for example, here, when your beam is failing and your concrete reaches the ultimate stress at the top fiber. This is the only time in the lifetime or in the assumed lifetime of a member where we need the compressive strength. So only for the load-bearing capacity. And of course, we also needed to give the concrete a name, to have a number that we can work with in our structural design. So we like to call it 40 MPa, put it into the program, and then we know that we have something that we can work with. So it's a naming convention for the concrete. It's a 40 MPa concrete. And lastly, very important, we use it for quality control. So it gives us a measure of specifying a value, and engineers love that. We like to specify a value, but that only makes sense if we have a test method to actually see whether that value was attained. And we need compressive strength for nothing else. Those are the only justifications for calling for a certain compressive strength. And if your structural design asks for 25 MPa, it makes absolute 0 sense to use a 30 MPa concrete. Don't do it. You're wasting your money and you're making the performance worse. So we can't use strength as an indicator for quality. We can't use it as an indicator for durability, and certainly not as an indicator of general high performance. And the reasons, or some of the reasons, are higher strength normally comes with a higher cement content. Higher cement content gives you higher chance of thermal stresses from hydration heat development, which can increase the risk of cracking. Your concrete, of course, is no longer sustainable, or is less sustainable if you add more cement. It's much more expensive, and higher cement contents, for example, also increase the risk of ASR. And also the risk of shrinkage cracking is increased. Shrinkage cracking depends on the number of factors. If your strength is higher, then your cracking resistance is higher. That is good. So higher compressive strength means higher tensile strength, higher cracking resistance. That is good. In the same time, your stress development depends on your elastic modulus and on your creep. And you can see here in the gray box, that is a modified version of Hooke's law. So your stress equals strain times the elastic modulus, and that is reduced by the creep factor. And here, a higher concrete strength typically comes with a higher elastic modulus, which gives you higher stresses. It comes with lower creep, which also gives you higher stresses. So the overall effect of using a higher strength is that you increase the risk of cracking. And to give you one example of what this means for the performance of structures, here we looked at a power plant in South Africa, which had 2 chimneys. Was built about 70 years ago. Both chimneys had the same age, the same concrete type, which we tested chemically, the same cover, the same exposure, but they had different strength. Maybe they, by accident, made the one chimney not as strong as they should have. And looking at the performance that we measured on that structure, so we're looking at the west and east chimney, you can see they had the same cover depth of around 35 millimeters, which is not too bad. They had different resistivities, which link to the different strength. Resistivity is a measure of how fast electricity can flow through the concrete. And typically, higher strength concrete gives you higher resistivity, which also gives you a higher resistance against reinforcement corrosion. So the West Tower, having 23 MPa, had a lower resistivity compared to the East Tower, which had twice the strength and also higher resistivity. The carbonation depth measured on the West was much higher than the East, which is because a more dense concrete, the 47 MPa one, will carbonate slower. So that's good. But in the same time, the high strength chimney was full of cracks. Cracks were all over the place, with crack spacings of around 1.1 to 3.1 meters and crack width up to about 0.8 millimeters. So quite severe shrinkage cracking. Whereas the West Tower, the low strength concrete, had hardly any cracks at all. And the result was that the low strength tower had hardly any damage, whereas the East Tower, the high strength, the perceived high quality tower, even though it had better concrete properties as such in terms of carbonation resistance and resistivity, showed much more damage. And here are some pictures of that. So the lessons to be learned here is that it's not just a scientific gimmick to do these calculations, but higher strength will give you, in some situations, poorer performance. So don't go the route assuming that by increasing the strength, you can improve the performance of your concrete, because you can't. So looking at service life design for reinforced concrete structures, typically we look at the 2 or 3 stage service life model. Looking at deterioration, we typically divide this into the corrosion initiation period and the corrosion propagation period. In the initiation periods, which can last 5 years, 10 years, 30 years, depending on the quality of your concrete and whether it's cracked or not, and depending on the cover depth. In the initiation period, you get mechanisms like chloride ingress and carbonation into your concrete. And typically, this is not connected to any damage. Only if, for example, chlorides have reached the steel in sufficient concentration to destroy the passive layer that I mentioned earlier, will reinforcement corrosion start. And once reinforcement corrosion has started, we talk about the propagation period. And this is sometimes divided into propagation and acceleration period, which then it becomes a 3-stage service life model. And in the propagation period, you get cracking, delamination, accelerated ingress of chlorides, for example, and reinforcement corrosion, which then eventually might lead to loss in service life of your structure. And looking at the durability design approaches, most of the approaches link to the initiation stage. So through our design, our concrete mix design, and through specifying certain construction procedures, we are trying to minimize the ingress of chlorides, or we try to minimize carbonation of the concrete through the lifetime that we want. So if we have a 50-year service life design, and we use this approach, for example, in the marine environment, and typically we are aiming at making sure that we stay in the chloride in the reinforcement initiation period for the first 50 years of the lifetime of the structure. So in terms of durability indicators, or the things that we need to specify and measure as engineers, we talk about the resistance to carbonation and the resistance to chloride ingress. And we use these as input parameters into our models. Once we've done that, we can specify limiting values for these parameters. And this can be done in the design stage only to develop suitable mixes, or in a more coherent and rational approach, we also use it for quality control. So we have now designed the concrete, we have specified a certain value, we have achieved that value in the mixed design stage. And once the structure has been built, we can control whether this value has actually been achieved or not. And looking at test methods to characterize our concrete for durability. Here we use durability indicators, which are measurable material properties that can be used to predict the concrete's performance, meaning its resistance against deterioration. And most commonly, these could include transport properties or performance simulation tests. Now, performance simulation tests, for example, the typical ones that we use are bulk diffusion and the accelerated carbonation chamber. In the bulk diffusion test, we expose a concrete sample to a salt solution and we measure chloride ingress over time, which tells us the chloride ingress resistance of the concrete. And quite similar, in the carbonation chamber, we have an increased carbon dioxide concentration, and we measure how fast the concrete carbonates over time. And these are great methods because they give us a direct handle on the resistance of the concrete against these mechanisms. The problem is that they take a lot of time. So we can use them in research, but we can't use them for mixed design and quality control because these tests take about 3 to 4 months, and we can't wait that long before we know whether things worked well on site or not. So here we look at transport properties, and this is also what we use in South Africa for our approach. And here we talk about permeability, sorptivity, resistivity, conductivity, and these things. And we could give a whole different lecture on transport properties, but just for you to understand that these test methods basically link to the pore structure of the concrete, the physical pore structure of the concrete, and also the resistivity and conductivity test linked to the chemical makeup of the pore solution. And with those characteristics of the physical and chemical makeup of the concrete pores, we can predict the ingress of chlorides, and we can predict carbonation into concrete, and then use this to quantify the concrete in terms of its durability properties. And the most prominent one used in South Africa is the oxygen permeability index test, the OPI test. You can see here a schematic of how this works. On the right, you see a photograph of a permeameter. So essentially, we have a concrete sample which is sitting in a silicon ring, which gets put into the permeameter. And this is all very tight, very airtight. And then the permeameter gets put under pressure. And it's a 10 bar pressure, 100 kilopascal pressure in the permeameter. And this is introduced with pumping oxygen into the permeameter. And then the only way for the oxygen to escape is through the concrete sample. And of course, the more dense the concrete is, the slower the oxygen will progress through the concrete, and the lower the permeability will be. So we essentially measure the permeability of the concrete under an applied gas pressure. And we interpret the resulting coefficient of permeability, which is calculated with this ugly equation there, in terms of the negative logarithmic value of that coefficient. What that means is that we express the coefficient of permeability in values typically between 8.5 for poor quality concrete to 10.8. But this being on a logarithmic scale means that 1 order of magnitude is given if the OPI increases or changes by 1. Meaning, for example, if you have an OPI of 9 compared to an OPI of 10, then the concrete that has an OPI of 10 will be 10 times less permeable than the concrete with an OPI of 10. Or like in this example, typically a good quality concrete might have an OPI of 10.3, whereas a more low quality concrete might have an OPI of 9.0. In that case, the concrete with the OPI of 9.0 is around 20 times as permeable as the concrete with an OPI of 10.3. And in the early days, this was used to simply call the concrete by name, say this is excellent concrete or good concrete, poor concrete, very poor concrete. And that has worked in the first few years, maybe 20, 25 years ago, until engineers said, look, we want to have more of a handle of service life design using these methods. And then a lot of good research was done. For example, here, some research we did at UCT about 10 years ago, where we could link the permeability coefficient to the carbonation coefficient, depending also on the binder type, because essentially carbonation doesn't just depend on the physical pore structure, which is what you measure with the OPI test. It also depends on the chemical makeup of the pore solution, of the pore structure. So we could establish for different binder types the correlation between the permeability coefficient, the OPI value, and the carbonation resistance for your structures in different environments. And all that good research has then led to the approach that is being used at the moment in industry also. So first, as I mentioned, you select the design environment and you choose the expected service life duration. Then concrete mixes are designed and tested to see whether they conform to the durability index specifications. And during or after production, the structure can be investigated to see whether you have compliance with the specified values. And the nice thing about this is you can optimize your concrete mix according to your requirements. You can make it in any way you want, essentially, if you just follow the prescriptive, the performance-based design alone. And the client can measure whether the quality supplied is the quality that was actually required. And if you look at the OPI test, the environmental exposure classes that need to be considered, or for which the OPI test needs to be considered, are the XC classes, which are the carbonation exposure classes. And in South Africa, essentially, we specify OPI values for exposure classes XC3 and XC4, which are the ones where carbonation typically occurs fastest. And I've seen that Philip Ronne is here in the audience. He will possibly he would possibly want to update on this. This is a slightly older version of the table, but the same principles still apply. So you can see here the Sunroad specifications that allow you for a certain exposure environment to trade off cover depth versus concrete quality. So for example, if you're in the most severe environmental exposure, XC4, and you work with a cover depth of 40 millimeters, then the typical minimum OPI that is required is 9.6. But if you can increase your cover to 50 millimeters, you can allow a lower concrete quality indicated by a lower OPI value. So this approach also allows us to basically combine the concrete properties with the cover depth to come to the best solution for this particular structure. And now, just one more point on durability. Looking at this structure here, this is the silo structure in Cape Town in the V&A waterfront, which a few years ago looked like this. I always looked at the structure with great interest when I was having boat rides with my kids, and took this picture about 15 years ago. And all those black spots indicate delaminations on the structure, where reinforcement corrosion had led to chunks of concrete falling down, the steel was exposed and was corroding. And that structure was subsequently repaired about 10 years ago. And you can see all the patch repairs here on the surface. And typically, if you have a structure that is as old as this one, I believe it's about 100 years old, that shows so much reinforcement corrosion damage, then even after patch repair, you would expect to come back every 5 years and do more and more and more patch repairs in regular intervals. Now, and I expected this to happen here also. And this is a recent photograph, and you see very few new delaminations, and there was no further spalling. There's hardly any steel exposed. So, and the reason for the great performance of this particular structure after repair is that they applied a hydrophobic sealant, which keeps out the moisture, the water. If you keep out the water, even if the concrete is chloride contaminated, reinforcement corrosion can't proceed because water is needed in the reaction. So by simply, and I say simply because it is fast, it's quite cost effective, and it's easy. You can spray it, you can brush it on. So by simply coating the structure with a hydrophobic sealant has provided a lot of durability to this structure. And if we would only use these materials to protect all of our new infrastructure, we would keep out the water throughout the lifetime of the structure. We would keep out chlorides throughout their lifetime. And we would probably prevent reinforcement corrosion altogether. So in terms of designing for durability, one very good approach is always what is called avoidance of deterioration, keeping the stuff out that can cause the problems. And with that, a bit of a research outlook. So these are the things we are working on at the moment at UCT. We are refining a durability index approach in that we are trying to integrate non-destructive in situ methods for quality control of structures. We are working on our service life models for carbonation and chloride ingress, and also to make them easier and more user-friendly for engineers. We are busy understanding modern binder types, especially limestone, calcine, clay cements, in terms of the durability properties, which look really positive. We are looking into service life extension using hydrophobic systems. ASR research is ongoing, and a lot is being done on that in terms of mechanisms, testing specifications, and so on. And we will continue working on condition assessment and concrete repair, essentially. And this brings me to the conclusion of this presentation. So durability can be provided based on good service life design, understanding the requirements in terms of service life duration, and looking at your environmental exposure, and then selecting adequate materials and good construction quality. We spoke about the limitations of using compressive strength as a quality indicator, and I will keep saying the same thing here for the next 20 years until I retire. And I've said it for the last 20 years. We must stop using compressive strength as a quality indicator. Higher strength means lower quality. You need to get the strength that is the design strength. If 40 MPa is asked for, you need to get 40, otherwise your structure isn't safe. But you don't want more than that. Rebar corrosion is the largest problem with our infrastructure, and we spoke about prescriptive versus performance-based design approaches and the South African approach, and also a little bit about surface protection. So that was essentially a condensed version of a one-week postgrad course, and I hope that you did, in fact, learn something. So thank you very much for your attention.
Thank you very much, Hans. I really enjoyed that. And I think we can give him a round of applause wherever you are without putting your mic on. Oh, yes, you can do it on the applause button. Thank you, Hans. I really appreciate that. You got a 4-hour or actually a week presentations all squashed into 1 hour. Well done.
Thank you, Billy.
I think we all learned a lot. I learned some of the basics over again. That's really, really nice. But now I think we've got an opportunity for questions. Is there anybody that's got a question? I see
Grant Harley and Mr. Mainkeys have their hands up, Billy.
Yeah, Mainkeys is first. If you can go first, Mr. Mainkeys. On my list, it was first.
That was an accidental hand. Thank you.
Okay. Grant Harley.
Firstly, thanks very much, Prof. That was very enlightening. I've got 2 questions. The one is on the case study with the power station and the stacks that you looked at. Do you think that the cracking was more plastic shrinkage, so short-term, or drying shrinkage, more of a long-term cracking effect? And do you think, this is part of the same question, that with today's modern kind of admixtures for reducing water content, that it would be as relevant today, the argument with strength? So that's the one question. And then the other question is, my understanding is that the correlations between OPI and carbonation are based on immature concrete. What would you recommend for trying to determine the resistance of carbonation for existing carbonation resistance for existing and mature concrete?
Okay, cool. Thank you very much. I'll answer the first question first. So in terms of the cracking that was due to drying shrinkage, you would expect plastic shrinkage only on surfaces that are exposed to the environment after being cast. Whereas we looked at the surfaces, at the circumferential surfaces, so those that were exposed to the formwork. So the shrinkage the cracking that we saw there was due to drying shrinkage, which typically occurs in the first couple of months of the lifetime of the structure. So those cracks would have been there probably after 3-4 months and would have over the lifetime facilitated the ingress of, in this case, carbonation, water, all those things that cause reinforcement corrosion. Now, in terms of the admixtures that can be used to reduce water content, absolutely. So that can be done to make sure the concrete has got less shrinkage now. But I think we don't really make much concrete anymore these days without admixtures. And the same principles still apply. If you have a higher strength concrete, no matter what is in it in terms of admixtures, you have a higher risk of cracking. And we've tested lots of structures, lots of different concrete mixes. That was one of our focus areas, the influence of strength of shrinkage cracking over the years. And that trend is absolutely clear, even with modern concretes and with admixtures, even with fibers, with different curing methods, with different anything. The higher the strength, the higher the risk of cracking. So that is still valid. In terms of your question on OPI versus carbonation, we have not just done the research on immature concrete. Even 25 years ago, the early work by James McKechnie, he looked at OPI values obtained in the lab compared to the carbonation of concrete that was many years old. And in our more recent, typically PhD projects, our PhD students exposed samples for up to 4 years in different environments all over in South Africa. And we measured the development of the OPI value over time and compared it to the carbonation depth development over time. So early work was done on immature concrete, that's true, but the knowledge we have these days is based on site observations also and on actually quite old concretes. So those models have been refined to a very large extent.
Right, thank you.
Thank you. Before I get to the next question, something I didn't mention in the beginning, we want to expand this concrete class to structural engineering as well. How to do a beam with strut and tie, or how to do shear design with strut and tie or something like that. That's just one topic we could have. If you have, there's a number of structural engineers in the audience. If you've got any idea of a topic, we must find somebody to talk about in structural engineering. It can be very basic. Just type it in the chat. We'll record it. And then hopefully I'll be able to do that in the future concrete class series. We'll be able to include a lot of structural engineering questions as well. But okay, we've got a question from Dean Swanepoel.
Good afternoon, Prof. Dean Swanepoel here from Gulf Engineering from the Maputo Bridge. Hope you're doing well.
Thank you.
Just a quick question. When we do our concrete designs and so on, obviously we've got our design strength, and then with then we get the target strength. So it's your opinion that we cannot reject the concrete if it does not get the design strength. I mean, the target strength, if you get the design strength, we can leave it as such. Is that correct? We don't have to use the target strength for acceptance control.
No, sorry. No. That's not what I meant. Sorry. So when I say 40 MPa concrete, I said don't exceed the 40 MPa. But the 40 MPa design strength comes with a certain target strength, of course. And typically that would be something like 48 MPa. But the target strength is there to make sure that 95% of your concrete samples reach the 40 MPa. So if your design strength, your characteristic strength is 40 MPa, then you will continue to aim at a target strength of 48 MPa or 45 MPa, depending on your quality control. But the point I'm making is that very often contractors and even engineers say, oh, let's put more cement in there just to be on the safe side. So then the 40 MPa concrete, which is 48 target strength, becomes a 50 MPa with maybe 58 target strength, and that is the problem. But of course, the common rules between characteristic strength and target strength fully apply.
Okay, so that's fine. So you do statistic analysis and you see you've got 49, 50, and then you reduce your cement content so that you have at least your 95% of your target strength then.
Exactly. So typically, I mean, your target strength is a function of your quality control. And I say 8 MPa because that is, I think, what the South African standards suggest for good quality control. But I'm aware that most concrete producers have better quality control than that. So they might use a target strength of maybe 40 plus 3 MPa. And once you have done enough mixes and you know about your statistical distribution, you can, of course, optimize your mix. So maybe you can work with a target strength of 45 MPa on a 40 MPa concrete. And that would be a good approach here.
Okay, thanks. So we in the middle of the bush, and our contract is not the best. They use volume batching, so we rather, if we do the target analysis, we work according to the SATCC, which they don't do a target strength. So then it's more or less, say, 40 plus 11 MPa that we should actually get. But obviously, in this case, it's miles to highway.
Yeah, but also, I mean, just to not create the wrong impression, if your quality control is such that your margin is 11 MPa, then you must use it. Absolutely. But I'm saying that the basis shouldn't change. You shouldn't use a 40 MPa concrete and say, let's do a 50 MPa because you think it gives you better quality. And if your margin is 11 MPa and you measure 51 MPa on a 40, then that is still a 40 MPa concrete, of course.
Exactly. Okay, thanks very much, Prof. Thanks for the
presentation. Okay. Thank you, Matteo.
Hi, Prof.
Matteo.
Both Profs. Hi, Billy. Hi, Hans. How are you? Thank you for the presentation. It brought me back. I was expecting to see a few photos of me measuring concrete cover on the jetties of Walvis Bay, but I think you've had many more people to torture between then and now.
I did. Thank you.
Prof, I've got two questions. One was related to one of your slides when you say, there's no, if I understood you correctly, you said there's no actual proper link between water binder ratio and durability. And I was just wondering if I misunderstood that or if you can elaborate on that, because my understanding is that a low water binder ratio in general gives you a denser concrete mix, which is more beneficial to durability. And then if you look at the constituents, so whether you have supplementary cementitious binders or not, that mix then can become more homogeneous, which also helps you with durability. That's question one. And then question two was related to this last question you answered in terms of target strength versus characteristic strength. But with the cements we use nowadays, especially with the 52.5s, I've had issues or I've had projects where I'll specify a characteristic strength of 35 MPa. So you ideally need to be getting a target strength of 40 or 42. But at 28 days, I'm getting 60 plus. And for me, especially in the field of liquid retaining structures, where you're trying to not have excessive strengths because you're trying to reduce thermal effects, that is a problem. That can be quite a significant problem. So, how do we bypass that, or how do we take better care of that in terms of the standards maybe need to be updated, or characteristics versus target versus what you actually get, especially with newer materials or the newer cement materials? I'm not formulating my questions really well, but I'm hoping you understand what I'm trying to ask.
No, I am. Thank you, Matteo. Trust an ex-UCT student to ask all the challenging questions, so well done. I'm going to answer your last question first. So I think One could take the hard approach and say that you can also specify a maximum strength, and you penalize the contractor when the strength is too low, as is common, but also when the strength is too high. Now, I don't think that is the approach we should take, because I think contractors have it difficult enough with us engineers. I think you need to work together with the contractor and the concrete producer to make them understand that you really want to have a strength as close to your design strength as possible. Because I believe that your 60 MPa on the 35 MPa concrete comes from the belief that they will give you better quality. They have a better safety margin if they produce higher strength. And it's so easy to do. They just put more cement in there. And it also comes from the situation where many engineers are quite harsh with the contractors and producers when the strength results aren't met. So they're putting in a safety margin to make sure they are okay. I think you should tell them that, of course, the strength must always be reached. Your 40 MPa or your 35 must be 35. But my advice to you would be, make sure that you need 35 MPa from a structural point of view, because you don't need 35 for anything else. If your structure works with 25, specify 25. 35 will not be better. It'll be worse. And then make your contractor understand that you don't want higher strength, and give them maybe an incentive to do that. I think the reason that they give you 60 comes from a misunderstanding that they are safer when they do that. That's my answer to the second question. And then the first one, yes, of course, you're right. If we test different concretes in the lab and we have a lower water binder ratio, higher strength, that will give us lower permeability. And we can also test lower carbonation, lower chloride ingress, and all that. So yes, there is a link between water binder ratio and durability. I fully agree. However, with respect to the standards, now so you now tell me you want to have a 35 MPa concrete, but that code might tell you you need to have a 45 MPa concrete for that exposure class. So then you're moving away from your 35 to a 45. And my point is that does not improve the durability. Yeah. Because if you unnecessarily increase the strength, then you get all these other issues of hydration need, cracking, and you mentioned them yourself. That is where this correlation between water binder ratio and durability gets lost. I can test any day in the lab that the lower water binder ratio is less permeable, but it's not true it's not sensible how this was translated into the design, where you have a minimum strength, a minimum water binder ratio for a certain exposure.
Yeah.
That's where this comes from.
Yeah, thank you. That makes sense.
Thank you very much. I think we're going to end it here. It's already almost 4:15. I checked the attendance. It was 75, so this is a new record. Congratulations, Hans.
Thank you.
So we're going from strength to strength. So we'll have to see how it goes next time. Everybody, thank you very much. Appreciate for listening. Thank you, Hans, for your presentation and your time and all the effort you put into there. And thank you and good night. Or good afternoon and then good night.
Good night.
Thank you.
Thank you so much. Bye-bye.
Bye-bye.